So we'd like to talk about an example of using directed line segments. So we have here as a setup. Notice that we have 4 points in space, P, Q, R, and S, and we want to show that the directed line segment from P to Q is equivalent to the line segment from R to S. And you may look at this and say, well, they're not the same. They're not low. They're shifted. They're in different places. They kind of look similar, but they're not overlapping. How can they be the same? Well, when we talk about vectors, vectors are considered the same if they have the same magnitude and they have the same. In 2D, we can think of it as slope. But as we move into 3D, you want to think of it really in terms of the change in components on each dimension. So by doing that, we're gonna show that PQ equals RS. The first thing, and probably the easiest thing to do from this point, is get some intuition. Look at these things. Do these look like equivalent vectors? Well, they look like they have the same slope, and they look to be, if I'm eyeballing it, they're about the same length. But how can we do this mathematically? How can we figure out a way to talk about this in a way that's precise? So to do that, let's go ahead and determine if the components are equivalent. So let's see if the x differences are equivalent. So we have P to Q. So the x component of Q minus the x component of P is 4. Okay, well let's get the y component of Q and P. So we have 5 minus 2 is 3. So our components are 4 and 3. What that tells me is that the vector components of PQ are 4 and 3. And we're going to talk about that more as we go along. So let's go ahead and get the vector components of R and S. Let's do S. Now remember, the order is important. The order is super important here. Remember that vectors are all about direction. So if I do Q minus P, I can't do R minus S. I have to do them in the order that they came in. So if I do Q minus P, I have to do S minus R if I'm comparing them. Now, this is the way you should be thinking about it in general, but if you're just doing comparisons, it doesn't really matter as long as you keep the order the same. But I would recommend, just for thinking about things in the way that they're supposed to be all the time, always go sort of back to front, right? You go from finish to start. That tells you how far you've gone, right? If you end up one location, you started one location, you subtract from where you are to where you were to tell you how far you've gone. So if I do S, the component of X, the X component of S minus the X component of R, well, that's 4 minus 0. And if I do the Y component, I get 3 minus 0, which is 3. Now that's pretty easy, right? If you're at the origin, you've traveled 4 and 3 distance, right? Simple. But what I notice is I have matching pairs. So since I have matching pairs, I actually already know that they're equivalent, which is nice. So what you can do if you're comparing to see whether or not two vectors are equivalent, two directed line segments are equivalent, is you can compare their components. And as long as they're components, if any one of them doesn't match, you're done. You say, they don't match. they're not the same vector. It's simple. You just work your way down the line. But another way to check that's really a good sanity check in kind of the greater world of how we do vectors, and a good practice for those of you who may go on to do things with vectors in your careers. One big thing to always check is magnitude, because a lot of times you can find out information from magnitude that you didn't think was there. So if two vectors have the same magnitude, maybe they're the same vector, but there's something a little wrong. But that's kind of beyond the scope of what we want to talk about right now. But for practice, we want to get these magnitudes. So if I get the magnitude of PQ, it's literally this, it's these, right? It's these components. It's the difference in X and the difference in Y. And we take the square root. So we have 4 squared plus 3 squared. Well, I mean, you should recognize this. It's a standard 3, 4, 5 triangle. And we know that PQ and RS are going to have the same components. So if they have the same components and they have the same magnitude, again, if they have the same components, they're going to have the same magnitude. But if they have that same magnitude, you're done. That's it. No stress, no problems. So that's really how you compare vectors in any space, whether it's 2D, whether it's 3D. It could be 10-dimensional space. When we deal with 10-dimensional space, well, a really good example of that is in the fields of things like machine learning. So we may be dealing with 10, 100, actually a lot of times it's thousands of quantity of different things that they're tracking at any given moment. And we want to make sure that if two vectors are the same, well, we don't need that extra data, because it doesn't give us anything additional if I have this and I have that. Or it may give us exactly the data we want because we want to show that this equals to that. So there's a lot of dimensional spaces out there. In space, we usually only deal with 2, maybe 3 dimensions of space. But in the real world, dimensional data goes all over the place.